Hello, everyone. Today we're going to talk about detecting group 1 cations. So there are 5 groups involved in cations, but today we are just going to talk about the group 1 cations. So how do we detect the elements involved in group 1 cations? And what are the elements that are involved in it? So let us see a chart which I retrieved from a website which I will indicate later. But this graphs or this chart or diagram shows the processes that are involved in detecting group one ions. So let's see now. So the 3 elements that are involved in group one ions are the silver, mercury, and lead. So the question now is, let's say there is a solution. And that solution is in aqueous form. So to isolate these 3 from that solution, we have to do or we have to add many reagents for them to be separated by from the solution and from one another. So that solution, let me say that it includes or it has or it contains all the group 5 or all the groups that are included in cations, which is the group 1, 2, 3, and 4, and 5. So the only thing that we want to do is separate group 1 cations from the rest of the solution. So to do that, we add here 6 molarity hydrochloric acid. And not just hydrochloric acid, it must be diluted. What is the purpose of that? So the purpose is to make sure that the elements or the cations will become solid or they will be insoluble solids. So now that we add the hydrochloric acid, the other things to do is centrifuge and decant. So what do these 2 words mean? So centrifuge kinda mean that we have to somehow shake the solution. We shake it in order for the in order for these 3 elements to be isolated from the solution. So how do we do that? First, remember that when we add hydrochloric acid, it will form a white precipitate. A white precipitate is in a solid form. So it will appear to us that there is a white color in that solution. In that white is the white precipitate solid, which include the silver, mercury, and the lead. These 3 elements in group 1 cations. So by centrifuging it, the solution, we isolate the solid precipitate, wet precipitate, for it to, in order for it uh, to be concentrated at the bottom of the solution, so that it will sit at the bottom and the liquid or the rest of the solution will rest at the top. So what is the purpose of that? We'll understand in the next step that we do, which is here decant or decantation. In decantation, in decanting the solution, we just have to pour the liquid which is at the top or which is at the top of the solution in order for the solid precipitate, which is the white precipitate, to remain at the beaker. Let's say it is in the beaker. So now that we separated the white precipitate in this solution as shown here. So we have two resulting arrows. First is the white precipitate, and the second one is the rest of the solution. And this solution that we discarded by decanting it in another beaker, let's say, it contains all the other cations that we can detect later. So this includes the group 2, 3, 4, and 5 cations. So now our attention will focus on separating or on detecting the three cations in group 1, which now in a form of a solid white precipitate. So not just only that, but as we can see here, it is in a solid precipitate wherein it is in each of the element has the chlorine element, which now we can read as silver chloride, mercury chloride, and the lead chloride. So the other thing that we will do here, imagine that we have this solid precipitate, white precipitate in a in a in a beaker, let's say. The other thing that we have to do in order for them to be separated from one another, by them I mean the silver chloride, the mercury chloride, and the lead chloride, which we will separate them one by one in order for us to say that there is really is a silver in the solution and there is a mercury and a lead in the solution. So the first thing we do to separate them in that precipitate is adding hot water. So the purpose of this hot water is because there is one element, one cations element in that precipitate that is soluble when in hot water. So that element is the lead. So lead chloride will become or will return back into an aqueous solution. So when it returned back into being an aqueous solution, the other two elements, which are the silver and the mercury chloride, will remain as solid white precipitate. So the other thing that we will do again is centrifuge and decant. We some kind of shake it and then for the top liquid or the top aqueous solution in another container so that the thing that will remain in the beaker, let's say, is the white precipitate which contains the silver here as shown and the mercury. So what happened to the aqueous solution now that is which is the which contains the lead? So the other arrow points here, it shows the lead being in a solution after the hot water is added. So what happened really here actually is that the lead chloride is separated into two. So as I mentioned earlier, it just returned back into being an aqueous solution, which means that it will return back into being a lead cations, and then the chlorine that was present a while ago will also be separated and will be also in an aqueous solution. So meaning in this solution there is a lead and a chlorine elements. So the other thing that we do for us to be able to prove that there really is a lead in the solution that we separated from the solid precipitate, which is in this side, to prove that there is lead in this side of the solution, we will add potassium chromate. So it is not mentioned here, actually, the potassium, but I think it's because the chromate is the only one that will react with the lead, which forms lead chromate. So it's actually potassium chromate. And when we add that substance, the chromate will react to lead as mentioned, and the resulting solution is yellow precipitate, which contains the lead. And that proves that there really is a lead in that solution when we see a yellow precipitate in that solution. So now that we proved that there really is a lead cations in this solution, the remaining things that we have to do is to prove the existence of the silver and hydrogen respectively. So first, to do that, we will have to separate again these two elements from one another. So how do we do that? Here, as indicated, we will add 6 molarity of ammonia, and then we centrifuge it again and decant to separate them. So there will be two reactions. There will be two reactions that will happen as indicated by two arrows here on the left side and the right side and here in the left side. So let's talk about the reaction that will happen when we add ammonia into the white precipitate, which contains the silver and the mercury. Let's talk about the side of the mercury first. So what happens here is when we add ammonia, the silver will react in which the silver will appear to be a gray precipitate as indicated here, a gray precipitate. But in reality, it is not actually a just a gray precipitate because the actual occurrence here is that there is a white mercury, a black mercury, which is in a liquid form, in another substance which contains mercury, which is in a black form, which is in a black color and a solid form. And when we mix that two, it will appear to be gray. So that's the reason why when we see a gray precipitate in a solution after adding ammonia, it means that there is a mercury ions in the solution. So that proves that in the solution that we are in the sample that we are detecting whether there is a mercury, it means that there is really a mercury in the solution because we saw that a gray precipitate formed. So the other one or the last one that we will do now is prove whether there is a silver cations in the solution. So let's get back to adding to the addition of ammonia. So when we add ammonia to the white precipitate here, we add here ammonia, right? So when we add ammonia, the silver chloride will react in a way that this it will form a substance which is called which is named silver amine chloride complex. So it contains the three elements that we mentioned: the ammonia, the silver, and the chlorine. So these three are mixed to one another, and it is in an aqueous form, which means it is not solid. So the reason why we were able to separate these two here from one another is because we made the silver chloride to become an aqueous solution. So that aqueous solution is what we decanted, we pour in another container, which the solid white precipitate, or in which the gray precipitate of the mercury here remain. So now we are now focusing on this solution wherein the silver amine chloride complex is present in an aqueous form. So now that it is an aqueous form, what we want to do is to precipitate it again, to make it in a solid form, so that we can prove that there is really is a silver in that solution. So we do this by adding 6 molarity of nitric acid. So adding nitric acid, the nitric acid here will react to ammonia in the solution that I mentioned here, which is the silver amine chloride complex. So the ammonia here will be separated from the silver. So remember that there is still a chlorine. So what will happen now is that the chlorine and the silver will react to one another again. And what happens when the silver and the chlorine react? As we remember, as we did back in the first step, adding hydrochloric acid, which contains chlorine, will form a white precipitate of silver chloride. So what will happen now? The chlorine and the silver will react to one another, which will form a white precipitate, which is what we call as the silver chloride white precipitate. So that proves that when we see a white precipitate, it contains a silver cations. So one by one, we were able to prove that there is this cations which belongs to group 1 cations that are present in the solution. So that is for today, for this time. And thank you for listening.